You are listening to the Architect's Compass, navigating object-oriented design patterns and anti-patterns. Like and subscribe to keep up to date on our latest audiobooks. The Architect's Compass, navigating object-oriented design patterns and anti-patterns. The blueprint of better software, an introduction. Imagine you're handed a beautiful, intricate model of a grand building. Every piece fits perfectly, the structure is sound, and it inspires awe simply by its thoughtful construction. Now, imagine a pile of randomly stacked bricks, held together with flimsy glue, threatening to collapse at any moment. Which one would you prefer to work with? Which one would you feel confident investing your time and resources into? This analogy is profoundly relevant to software. In the world of programming, it's easy to focus solely on getting the code to work. Does it compile? Does it produce the correct output? Does it satisfy the immediate requirement? And while these are undeniably important questions, they are only part of the story. Software isn't just about making things work. It's about making them well-built. It's about craftsmanship and foresight. Just like physical buildings, software systems benefit immensely from thoughtful design. Good software design is the difference between a resilient, adaptable structure and a fragile, constantly crumbling mess. It makes software easier to understand, simpler to change without accidentally breaking existing functionality, and more resilient to future demands. Poor design, often accumulating what we call technical debt, can turn even the most promising project into a maintenance nightmare, consuming precious time, draining resources, and eroding the morale of the developers tasked with maintaining it. It's like building a house with low-quality materials, and then discovering that every pipe needs replacing within a year, or that simply adding a new window requires tearing down a structural wall. This is where the concept of design enters the realm of programming. Software designers, much like architects, don't just randomly stack code. They employ principles and patterns to construct systems that are not only functional, but also maintainable, scalable, and adaptable. Think of design patterns as the architectural blueprints of the software world. For centuries, physical architects didn't reinvent how to build strong arches, support heavy roofs, or arrange rooms for optimal flow every time they started a new building. Instead, they refined proven solutions to recurring structural or functional problems. Similarly, software design patterns are generalized, reusable solutions to common problems that crop up again and again in object-oriented programming. They are like a specialized toolbox, filled with proven carpentry joints or masonry techniques that have been tested and refined by countless builders before you. By adopting them, you gain a powerful, shorthand way to communicate complex design decisions, fostering a shared vocabulary among experienced developers. On the flip side, we have anti-patterns. These are recurring solutions that are, in fact, bad. They represent common mistakes and pitfalls that, while seeming reasonable at first glance, inevitably lead to disastrous outcomes. Recognizing an anti-pattern is like knowing what kind of structural defect will inevitably lead to a building's collapse. It's crucial knowledge for avoiding or correcting flawed design that might seem intuitive initially, but leads to significant long-term pain and technical debt. Learning about anti-patterns is as important as learning about patterns, because understanding what not to do can save you from a great deal of trouble and rework down the line. It's learning from the collective failures of others, so you don't have to experience them firsthand. Before we dive deep into these blueprints and pitfalls, let's quickly refresh our understanding of object-oriented programming, or OOP, which serves as the foundational paradigm for these concepts. OOP revolves around objects, which are like self-contained entities that combine data with behaviors. For instance, a car object might contain data like its color and speed, and have behaviors like accelerate or brake. These objects are created from classes, which act as their blueprints. A car class defines what every car object will look like and how it will behave. Within OOP, there are several core principles that enable the elegance and flexibility that patterns leverage. Encapsulation, for example, means hiding an object's internal workings and data, only exposing what's necessary for interaction. Think of it like a remote control for your TV. You press a button, and the TV responds, but you don't need to understand the complex circuitry inside the remote or the TV to use it. Inheritance, allows new classes to build upon existing ones, taking on their properties and behaviors, like a sports car inheriting many characteristics from a general car class, but adding its own unique features. Finally, polymorphism is the ability for different objects to respond to the same command in their own unique ways. If you have a turn-on button, pressing it on a light switch results in light, but pressing it on a computer results in the boot-up sequence. The intent is the same, but the specific action is tailored to the object. Design patterns often orchestrate these principles in powerful and elegant ways. By the end of this book, you'll not only understand what these patterns and anti-patterns are, but more importantly, when and why to thoughtfully use them or decisively avoid them. You'll gain a powerful new language to discuss software design, enabling you to construct more robust, flexible, and maintainable systems, and to collaborate more effectively and intelligently with your team. This journey will equip you with a compass to navigate the complex landscape of software development, guiding you toward better, more sustainable software architecture. Let's begin. Building blocks of object-oriented design, a refresher on principles. In our journey to understand the blueprints and pitfalls of software design, it's essential to ensure we're all speaking the same language when it comes to the fundamental building blocks. Object-oriented programming, OOP, forms the bedrock for design patterns, and a solid grasp of its core concepts and principles is indispensable. While briefly touched upon in the introduction, this chapter will delve a little deeper, setting the stage for why patterns exist and how they leverage these foundational ideas. At its heart, OOP aims to model real-world concepts as self-contained entities called objects. Think of an object as a compact capsule bundling both piece of information and the actions that can be performed related to that information. For example, a dog object might hold information like its breed and name, and also possess actions like bark or fetch. These objects are not created out of thin air. They are instances of classes, which serve as the blueprints or templates for creating objects. The dog class defines what every dog object will look like, what data it will contain, and what behaviors it will exhibit. Let's unpack the main pillars of OOP. First, there's encapsulation. This principle is about bundling data and the methods that operate on that data within a single unit, and, crucially, restricting direct access to some of the object's components. It's like a black box. You know what you can put in and what you can get out, but you don't need to know and ideally shouldn't be able to interfere with the inner workings. Imagine a car. You interact with the steering wheel, the pedals, and the gear shift. You don't directly manipulate the engine's pistons or the transmission's gears. Encapsulation ensures that an object's internal state is protected from external tampering, promoting data integrity and making the code easier to maintain because changes to internal implementation don't necessarily affect external users of the object. Next is abstraction. While closely related to encapsulation, abstraction focuses on showing only essential information and hiding the complex implementation details. It's about providing a simplified, conceptual view of something. When you use an ATM, you interact with a simplified interface, buttons for deposit, withdrawal, balance inquiry. You don't see the complex network communications, database queries, and security protocols happening behind the scenes. Abstraction allows developers to work with high-level concepts without getting bogged down in low-level specifics, improving clarity and managing complexity. Then comes inheritance. This is the mechanism where one class can acquire the properties and behaviors of another class. It's a way to establish a hierarchical relationship, expressing an is a relationship. For example, a sports car is a car. The sports car class would inherit all the common attributes and methods from the car class, like having wheels, a steering wheel, and methods for accelerating or braking. But it could also add its own unique characteristics, like a spoiler or a turbo boost method. Inheritance promotes code reuse and helps define a natural hierarchy within your software system. Finally, we have polymorphism. This word means many forms. In OOP, polymorphism allows objects of different classes to be treated as objects of a common type. It means that a single interface can be used to represent different underlying forms or types. Think of a print button. On a document, it prints text. On a photo editor, it prints an image. While the action is nominally the same, print, the specific way it's carried out depends on the type of object it's applied to. In programming, this means you can write code that operates on a generic type, and at runtime, the correct specialized behavior for the specific object will be invoked. This greatly enhances flexibility and allows for highly adaptable systems. Introducing the solid principles, your foundational rules for resilient design. While the 4 pillars of OOP provide the structure, the solid principles offer a set of guidelines for applying those OOP pillars effectively to build software that is robust, maintainable, and extensible. Coined by Robert C. Martin, these 5 principles are like the golden rules for creating clean, adaptable, object-oriented software. They serve as a compass, guiding you away from common pitfalls and towards designs that embrace change rather than resist it. Let's break down each letter of SOLID. S. Single Responsibility Principle, SRP. This principle states that a class or a module should have only one reason to change. In other words, it should have a single responsibility. Why it matters? Imagine a report generator class that is responsible for gathering data, formatting it, and then sending it via email. If the report format changes, you modify this class. If the email sending mechanism changes, you also modify this class. This means the class has multiple reasons to change. SRP suggests that formatting the report should be one responsibility, sending email another, and gathering data yet another. Analogy: think of a Swiss Army knife. It has many tools, but if the screwdriver breaks, you might have to replace the whole knife, impacting other tools like the bottle opener or blade. A better design separates tools, each with its own single purpose. A dedicated multi-bit screwdriver, a separate bottle opener, a separate knife. If one breaks, you replace only that specific tool, not everything else. Impact on design. Adhering to SRP leads to smaller, more focused classes that are easier to understand, test, and maintain. Changes are localized, reducing the risk of introducing unintended side effects elsewhere in the system. Open-Closed Principle, OCP. This principle suggests that software entities, classes, modules, functions should be open for extension, but closed for modification. Why it matters. This is about allowing new functionality to be added without altering existing, working code. When you modify existing code, you risk introducing bugs into previously stable parts of your system. Analogy. Consider a modern smartphone operating system. When you want a new feature, you typically download a new application from an app store. You don't have to rewrite the phone's core operating system or hardware. The operating system is closed to modification, you don't go in and change its code, but open to extension, you can add new apps. Impact on design. OCP encourages using abstract interfaces and polymorphic behavior. Instead of hard-coding specific implementations, you code against abstractions, allowing new implementations to be plugged in without changing the core logic. This is fundamental for building flexible and adaptable systems. Liskov Substitution Principle, LSB. This principle states that objects of a superclass should be replaceable with objects of its subclasses without breaking the application. Why it matters. This one is crucial for correct inheritance. If Class B is a subtype of Class A, then anywhere Class A is expected, an object of Class B should be usable without causing incorrect behavior. It's not just about syntactical correctness, but behavioral correctness. Analogy: imagine you have a method that expects to operate on a bird object, telling it to fly. If you then pass a penguin object, which is a type of bird, to this method, and the system crashes because penguins can't fly, you've violated LSB. A penguin object cannot substitute for a generic bird when the fly behavior is expected. Impact on design. LSB ensures that hierarchies are robust. It compels designers to think carefully about the behavioral contracts of their classes and interfaces, leading to more predictable and reliable polymorphism. Interface Segregation Principle, ISP. This principle advises that clients should not be forced to depend on interfaces they do not use. Put simply, many client-specific interfaces are better than one general-purpose interface. Why it matters. If an interface is too broad, clients who only need a small part of its functionality are exposed to methods they don't care about, and if any of those unused methods change or break, it still forces a change or recompilation in the client. Analogy: think about a universal remote control. If it has buttons for every possible device imaginable, TV, VCR, DVD, Blu-ray, projector, smart lights, smart thermostat, lawnmower, etc., and you only own a TV, most of those buttons are irrelevant to you. If the lawnmower button's function changes, it affects the whole remote and potentially requires an update even though you don't even have a lawnmower. ISB suggests creating smaller, specialized remotes interfaces for specific devices or functionalities. Impact on design. ISB promotes highly cohesive interfaces, reducing unnecessary dependencies and making systems more flexible and easier to maintain. D-dependency inversion principle, DIP. This principle states that high-level modules should not depend on low-level modules, but both should depend on abstractions. Also, abstractions should not depend on details, details should depend on abstractions. Why it matters. In traditional programming, high-level components, e.g. business logic, often directly use and depend on low-level components, e.g. database access, file I/O. This creates tight coupling. If the low-level component changes, the high-level one often has to change too, making the system inflexible. Analogy: imagine a wall plug and an appliance. The appliance, high-level module, e.g. a toaster, doesn't depend directly on a specific electrical outlet in your wall, low-level module. Instead, both depend on the abstract concept of a standardized electrical socket, the interface. You can plug your toaster into any compliant socket, whether from a wall, an extension cord, or a generator, without changing the toaster. Impact on design. DIP is crucial for building decoupled systems that are easy to test, swap out components, and evolve. It often involves using techniques like dependency injection, where dependencies are provided to a component rather than the component creating them itself. These 5 solid principles are not merely academic concepts. They are practical guidelines that, when applied thoughtfully, lead to software that is significantly easier to understand, test, extend, and maintain. They form the underlying philosophy that many design patterns embody and are essential for discerning good design from bad. As we explore design patterns in the following chapters, you'll see how these principles are woven into their very fabric, providing the why behind their structure and effectiveness. With these building blocks firmly in mind, you're now ready to identify common architectural flaws and then learn the proven solutions to building robust and elegant systems. When good code goes bad, understanding anti-patterns. You might have started a software project with the best intentions, aiming for clean, elegant code, diligently following best practices. Yet, as deadlines loom, requirements shift, new features pile up, and different developers contribute, a creeping chaos can set in. This chapter delves into the diseases that infest software, the anti-patterns, which are recurring bad solutions that, despite their apparent convenience in the short term, lead to technical debt, frustration, and ultimately, code that's a nightmare to maintain. Understanding anti-patterns is like learning from someone else's mistakes. They represent universally agreed upon common pitfalls in software design that consistently lead to negative outcomes. By recognizing them, you can avoid falling into these traps yourself, or, just as importantly, identify them in existing code bases and devise strategies for refactoring. Code smells. The early warning system. Before we identify the major diseases themselves, let's talk about code smells. These are surface-level indicators, like a strange, persistent odor in a house, that suggest a deeper problem underneath. A code smell isn't necessarily an anti-pattern by itself, but it's often a symptom that signals an anti-pattern is lurking nearby, or that the design is simply suboptimal. For instance, if you spot a method that goes on for hundreds of lines, trying to do too many things, that's a long method smell. Or if you see the exact same lines of code repeated in multiple places, that's duplicate code. Another common smell is feature envy, where a method in one class seems more interested in the data of another class than its own. These smells are not fatal on their own, but they are red flags that scream, "Look here, there might be a better way to do this, and ignoring me might lead to bigger problems." They are signals for where you might consider refactoring, perhaps by applying a design pattern. Now, let's explore some of the most common and damaging anti-patterns. The God object big ball of mud. The problem? Imagine a single, monstrous class or module in your software that knows and does everything. It's the God object. It controls too many things, has too many responsibilities, and everyone depends directly on it. If it were a person, it would be the ultimate micromanager who insists on doing everyone else's job, storing all the knowledge, and overseeing every detail. Analogy: think of a universal remote control that doesn't just control your TV, sound system, and lights, but also drives your car, cooks your dinner, files your taxes, and manages your personal finances. While theoretically convenient for one person in a very specific, isolated scenario, if that remote breaks, your entire life grinds to a halt. And if you want to add a new appliance or service, you have to completely redesign this one remote, making it even more complex and fragile. The God object is incredibly brittle. Changing one small function can have unpredictable, cascading effects across the entire system. It severely violates the single responsibility principle, making the system difficult to understand, test, and evolve. Consequences: high coupling. Everything in the system is connected to it, making independent development or replacement of parts nearly impossible. Low cohesion. It does too many unrelated things, making its purpose unclear and its internal logic complex. Difficult testing. You can't test a small part of it without setting up an enormous amount of context. Maintenance nightmares. Every change carries a high risk of breaking something else, leading to a vicious cycle of bug fixes that introduce more bugs. Slow development. Changes are slow and painful due to the interconnectedness. Spaghetti code. The problem? This isn't a specific architectural pattern, but rather a description of code that's highly disorganized, with complex and tangled control flow. It relies heavily on arbitrary jumps, like the infamous go-to statements found in older languages or convoluted conditional logic, making it nearly impossible to follow the logical path of execution. It's the precise opposite of a structured, modular design often seen in well-designed object-oriented systems. Analogy: envision a bowl of spaghetti. Every strand is intermingled with every other. Trying to pull out a single strand without disturbing the entire bowl is a futile, frustrating effort. Similarly, in spaghetti code, logic flows unpredictably, jumping from one section to another without clear boundaries or understandable reasons. Debugging feels like unwinding that tangled bowl, and adding new features feels like forcing a new strand into the already jumbled mess. Consequences: extremely difficult to read and understand. New developers will struggle immensely, and even the original author might forget the logic over time. Maintainability nightmare. Modifying behavior or fixing bugs often requires understanding the entire convoluted flow, leading to uncertainty and fear of change. High bug rate. The unpredictable flow makes it easy to introduce errors when attempting modifications. Untestable. Because logical units are not isolated, they cannot be tested independently. Lava flow. The problem: this anti-pattern describes the presence of dead or obsolete code that is still part of the system, even though it's no longer used or even understood. Like lava that has cooled and hardened, it's difficult to remove, but unlike actual lava, it serves no useful purpose. Analogy: imagine an old office building that has been renovated many times. Over the years, old electrical wiring, disconnected plumbing, and unused conduits from previous layouts remain embedded within the walls, just in case. No one dares to remove them because they might be connected to something vital, or because removing them could damage the structural integrity of the building. So they sit there, adding weight and confusion, making any future renovation development more complex and risky. Consequences: increased complexity. Developers have to navigate and understand unnecessary code, slowing down development and increasing cognitive load. Increased risk. Fear of breaking something by deleting old code prevents refactoring and improvement. Larger code base inflates the physical size of the code base, which can affect compilation times, deployment size, and overall system performance. Maintenance burden. While not actively used, it still needs to be reviewed, compiled, and managed, leading to wasted effort. Copy-paste programming. The problem? Instead of creating truly reusable functions, classes, or modules, developers simply copy existing blocks of code and paste them wherever similar functionality is needed. This creates rampant duplication throughout the codebase. The motivation is often speed. I need this functionality, I know where it exists, I'll just copy it. Analogy. Imagine building houses by literally cutting out sections from blueprints of old houses and taping them together, rather than designing standardized components like doors, windows, and roof trusses that can be used consistently across all designs. If you find a defect in a copied section, say, a faulty window design that leaks, you would have to manually find every instance of that copied window in every house you built and fix it. If you miss even one, the defect persists in your product line, creating inconsistent quality. Consequences: maintenance nightmare. A bug fix or an enhancement in one location requires finding and applying the same change to all duplicates. This is tedious, error-prone, and almost guarantees inconsistent behavior over time if a duplicate is missed. Code bloat. The overall size of the codebase unnecessarily increases, slowing down compilation, analysis, and understanding. Difficult to refactor. Large-scale changes become daunting because of the pervasive duplication. Inconsistent behavior. Over time, different copies of the same logic will inevitably diverge, leading to different parts of the system behaving unexpectedly. Golden hammer. The problem: this anti-pattern describes the tendency to use a familiar technology, tool, or solution, the golden hammer, for every problem, regardless of whether it's the most appropriate fit. It's born from comfort and an unwillingness to learn new approaches. To a hammer, everything looks like a nail. Analogy: imagine a skilled carpenter who owns a single, magnificent, gold-plated hammer. It's a beautiful tool, and they're incredibly proficient with it. However, they insist on using this hammer for every task: driving nails, tightening screws, sanding wood, even cutting planks. While they might eventually force a screw in with enough hammering, the result will be ugly and inefficient. The right tool for a screw is a screwdriver, and for cutting wood, a saw. Consequences: suboptimal solutions. The chosen solution isn't the best fit, leading to overengineering, underperformance, or excessive complexity. Missed opportunities. Better, simpler solutions are overlooked because of bias towards the golden hammer. Increased technical debt. Forcing a square peg into a round hole creates awkward, brittle code that will need extensive rework later. Wasted resources. Time, effort, and money are spent trying to bend a problem to fit the favored solution, rather than finding an efficient solution for the problem. Magic push button. The problem: this arises in user interface, UI, development, where all the business logic or complex calculations are crammed directly into the event handlers of UI elements, like a button's click event. The UI becomes inextricably tangled with the core application logic. Analogy: imagine you're in a restaurant and the menu is also the kitchen. When you order Caesar salad, the waiter doesn't just take your order. They literally chop the lettuce, mix the dressing, and plate the salad right there at your table, explaining every ingredient and process as they go, blocking the aisle and creating a mess. Every menu item has its entire preparation instructions glued onto its button. If you then want to serve the salad through a delivery app, you have to find and untangle all those instructions from the physical menu button. Consequences: difficult to test. The core logic is impossible to test independently of the UI. Poor reusability. The business logic cannot be reused by other parts of the application, e.g., a web service, a batch process, a different UI. Hard to modify. Changes to UI or business logic inevitably affect the other, leading to cascading problems. Violates SRP. A single UI element ends up with multiple responsibilities: presenting the UI and performing complex operations. The high price of bad design. These anti-patterns, individually and especially in combination, paint a grim picture. They are insidious. They start as small compromises or seemingly quick fixes, but they fester, accumulate, and mutate into what is commonly known as technical debt. Just like financial debt, technical debt accrues interest. The longer you put off fixing these design flaws, the more expensive and difficult it becomes to implement new features, fix bugs, or adapt to changing requirements. The interest manifests as slower development cycles, increased defect rates, demoralized teams, and ultimately, a system that becomes too fragile or too costly to evolve, leading to its eventual decline and replacement. Recognizing these anti-patterns is the first critical step toward building more robust and sustainable software. By understanding the common traps, you arm yourself with the knowledge to either avoid them in your new designs or to identify and refactor them in existing codebases. In the following chapters, we'll turn our attention from these common pitfalls to the elegant, proven solutions that design patterns offer, providing a roadmap for crafting truly maintainable and adaptable software. The genesis of objects' creational design, patterns. In the world of software, creating objects might seem like the simplest task. After all, you just tell the computer to make a new one, often with a straightforward command. But if not managed carefully, this seemingly simple act of creation can lead to tightly coupled code, restrict flexibility, and make your system hard to change. When one part of your program is overly concerned with how another part is created, they become intimately intertwined. This can make swapping out components, adding new types of objects, or changing the creation process a painful ordeal. This is where creational design patterns come into play. These patterns provide powerful control over how objects are instantiated, when they're created, and by whom. They are all about decoupling the client code, the part of your software that uses an object, from the concrete implementation of its creation. By abstracting the instantiation process, creational patterns add a layer of flexibility, allowing systems to be more adaptable to changing needs without significant reengineering. They solve the question, how can I create objects without specifying the exact class to be instantiated, given the surrounding context? Let's explore some of the most common and powerful creational patterns. Singleton. The problem: there are certain resources or components in a software system that should only ever have one instance throughout the application's lifetime. For example, a logging utility that writes all system events to a single file, a configuration manager that loads settings once and makes them universally available, or a single connection pool to a database that needs to be shared across many parts of the application. The challenge is to ensure that only one object exists and that all parts of the system access that exact same single instance. Analogy: consider the role of a country's president or prime minister. There can only be one president holding office at any given time. Every government agency, every citizen, and every foreign dignitary refers to the president, not a president. You don't accidentally create a second, separate president. The entire system for establishing leadership ensures a single, authoritative individual holds the office at any point, and everyone accesses that one individual for official matters. How it works verbally. The singleton pattern ensures that the class itself manages its single instance. Typically, the class responsible for the singleton will have a private way of creating itself, meaning no external code can directly use the new keyword to make another copy. Instead, it provides a public static method, often named something like getInstance or current, to retrieve its one true instance. This method checks if an instance already exists. The very first time it's called, it creates the instance if it doesn't already exist and stores it privately. On subsequent calls, it simply returns the already created, existing instance. This guarantees that only one ever exists throughout the application, and everyone gets access to the same one. Benefits: controlled access to a unique resource. Ensures that critical resources or managers are not duplicated, preventing conflicts or inconsistent states. Ensures consistency. All parts of the system interact with the same instance, guaranteeing consistent data or behavior for shared components. Resource savings. Can save resources by preventing multiple expensive object creations, such as database connections or configurations. Drawbacks can lead to tight coupling. Because many parts of the system might directly refer to this single point of access, it can become a global dependency, making parts of the system interdependent. Can complicate testing. Introducing global state via the singleton can make unit testing difficult, as tests might interfere with each other or require complex setup and teardown to isolate the singleton state. Often misused. Developers sometimes apply the singleton pattern when a simple dependency injection or passing an object around would suffice, leading to unnecessary complexity and rigidity. Use it only when truly one instance is required and its global accessibility is valuable. Factory method. The problem? You have a superclass or a framework that needs to create objects, but it shouldn't be hard-coded to create a very specific type of object. The exact type of object to be created should be determined by its subclasses, allowing for flexibility and extensibility without modifying the core system's creation logic. Your code needs to be able to create different types of related objects without knowing their exact classes in advance. Analogy: imagine a large bakery chain. The central management, which is like the superclass or framework, defines a general process for baking bread. But different regional bakeries, which act as subclasses, specialize in different kinds of bread. One produces sourdough, another rye, and another baguettes. The bake bread method, which we can call a factory method, is defined in the central plan as a placeholder. Each specific bakery then implements how to bake their specialty bread. The customer simply orders bread from the chain, and the appropriate bakery provides it without the customer needing to know the specific type of flour or yeast used. How it works, verbally. You define a method within an interface or an abstract class. Let's call it create product. This method is designed to return a generic type of product, e.g., bread. However, the actual implementation of which concrete product is created is left to subclasses. So, if you have a vehicle factory with an abstract create vehicle method, you can then create a car factory subclass that implements create vehicle to produce a car object, and a truck factory subclass that produces a truck object. The client code, the part of your system that needs a vehicle, only interacts with the generic vehicle factory interface and doesn't need to know the specific type of factory being used or exactly what kind of vehicle it's creating. It queries the factory and gets a vehicle object back. This way, adding a new type of vehicle, like a motorcycle, only requires creating a new motorcycle factory subclass without modifying the existing client code or the core vehicle factory. Benefits: decouples clients from concrete classes. The client code doesn't need to know the exact class of the object it's creating. It just knows it's asking a factory to produce an object that adheres to a particular interface. Allows for easily adding new product types. To introduce a new type of object, you typically only need to create a new concrete subclass that implements the factory method without altering existing code. This aligns perfectly with the open-closed principle, open for extension, closed for modification. Promotes consistency, ensures all objects are created uniformly following a set process, even if the specific implementation varies. Abstract factory. The problem? You need to create families of related or dependent objects without specifying their concrete classes. Your system might need to work with multiple families of products, and you want to ensure that compatible products are always used together. For instance, imagine a cross-platform user interface toolkit that needs to create consistent sets of UI elements: buttons, checkboxes, text fields. For Windows, Mac, and Linux, ensuring that a Windows button is always paired with a Windows checkbox and never accidentally a Mac button with a Linux checkbox. Analogy: think of a restaurant that offers different cuisines or themes, say Italian, Mexican, and Asian. Each cuisine offers a family of complementary dishes: an appetizer, a main course, and a dessert. If you order the Italian meal, you expect an Italian appetizer, an Italian main course, and an Italian dessert. You don't want a Mexican appetizer showing up with your Italian main course. The restaurant provides an abstract factory for meals and then specific factories: an Italian meal factory, a Mexican meal factory, and an Asian meal factory. Each of these specific factories ensures that all components supplied are from the same family. How it works, verbally. The abstract factory defines an interface for creating families of related objects, but it doesn't implement the creation itself. It might declare methods like create button, create checkbox, or create text field. Then, you have concrete factory classes that implement this abstract interface for each specific family. For example, a Windows UI factory would implement create button to return a Windows button, create checkbox to return a Windows checkbox, and so on. Similarly, a Mac UI factory would return Mac button, Mac checkbox, etc. The client code receives an instance of one of these concrete factories, e.g., either Windows UI factory or Mac UI factory, and then uses that factory to create all the necessary UI components. This ensures that all elements created from that factory are consistent within their theme. Benefits: ensures product consistency, guarantees that the objects created are compatible and belong to the same family. Client independence: the client code is decoupled from the concrete classes of the objects it creates and from the specific factory used. It only interacts with the abstract factory interface. Easy to swap families. You can easily swap one family of products for another by simply changing the concrete factory instance that the system uses. Builder. The problem? You need to construct a complex object that often has many optional parts or variations. The construction process itself can be intricate, involving many steps and configurations. If you try to do this all within a single constructor method, it can become unwieldy, difficult to read, and error-prone due to the sheer number of parameters. You also don't want the construction logic to be scattered across your client code. Analogy: imagine building a custom computer. You don't just say, "Give me a computer." You specify the processor, the amount of RAM, the type of hard drive, the graphics card, the operating system, and so on. There's a specific order to assembling these components, e.g., install the CPU before the cooler, install the OS after hardware is ready, and many parts are optional. A computer builder orchestrates these steps. You give the builder your specifications, and they systematically assemble the machine for you, handling all the intricate steps correctly. How it works, verbally. The builder pattern separates the construction of a complex object from its representation. It involves several key players. The builder, an interface that defines the steps required to build the parts of the complex object. It has methods like build part A, build part B, build part C, and a method to get result, which returns the fully assembled object. Concrete builders. These are specific implementations of the builder interface. A gaming computer builder might implement the build graphics card method with a high-end card, while an office computer builder might use an integrated graphics chip. Each concrete builder handles the specific details of building its particular variation of the complex object. The director. This is an optional component, sometimes omitted. Its job is to define the order of building steps. It works with the builder interface, telling it what parts to build and in what sequence, but leaves the details of how each part is built to the specific concrete builder. For example, a director might have a method construct standard computer that calls builder build processor, then builder build RAM, etc. The product, the complex object being built, e.g., the computer. The client code typically interacts with the director, if present, and a concrete builder. It instructs the director to build a specific variation of the product, or it directly manipulates the concrete builder by calling it step-by-step methods and then retrieves the final product. Benefits: separation of concerns. The construction logic is separated from the object's class, making both easier to understand and maintain. Step-by-step construction allows for fine-grained control over the construction process and enables building objects with varying levels of complexity. Reusability of construction code. The same building process, defined by the director, can be used with different builders to produce different representations of the product. Cleaner client code. Clients don't need to know the intricate details of object construction as the builder handles it. Creational patterns provide elegant solutions to the complexities of object instantiation. By applying them, you ensure that your code remains flexible, maintainable, and adaptable as your application grows and evolves. They are not just about making objects, but making them in a smart, controlled, and decoupled way. Assembling the architecture structural design patterns. Once we know how to create objects effectively, the next challenge is figuring out how to combine these objects and classes into larger, more flexible, and more efficient structures. This is where structural design patterns come into play. They address the question of, how can I compose objects and classes to form larger structures while maintaining flexibility and efficiency? Structural patterns focus on simplifying the relationships between disparate parts of your system. They help ensure that if you change one part, it doesn't necessarily force cascading changes throughout the entire system. They are about arrangement, organization, and creating new functionality by assembling existing components, rather than modifying their internal workings. Think of these patterns as the blueprints for robust and adaptable object graph constructions, allowing you to build complex systems from simpler, well-defined parts. Let's explore some of the most influential structural patterns. Adapter. The problem: you have two existing components or interfaces that should work together, but their interfaces are incompatible. One component offers a service, but its methods or expected input-output don't match what another component needs. Rather than changing the existing code of either component, which might be difficult, costly, or even impossible if they come from third-party libraries, you need a way to make them communicate. Analogy. Imagine you're traveling overseas and your electronic devices have two-pronged plugs, but the wall sockets in your hotel room are three-pronged. You don't want to rewire your device or the hotel's electrical system. Instead, you use a travel adapter. This adapter doesn't change your plug or the wall socket, it merely provides a compatible bridge between them, allowing your device to draw power from the different shaped socket. How it works, verbally. The adapter pattern works by creating a new class, the adapter, that translates the interface of one existing class, the adaptee, into another interface, the target, that clients expect. The target is the interface the client code expects to use. The adaptee is the existing class with the incompatible interface. The adapter class implements the target interface, meaning it has the methods the client expects. Inside these methods, the adapter then calls the equivalent methods of the adaptee, translating parameters and return values as needed. So, the client code interacts with the adapter as if it were a direct implementation of the target interface, and the adapter does the behind-the-scenes work of communicating with the adaptee. Benefits: reusability, allows the use of existing classes and components that might otherwise be incompatible. Flexibility, provides a clean way to integrate new or legacy code without modifying stable systems. Decoupling, keeps the client code separated from the internal implementation details of the adaptee. Decorator. The problem: you want to dynamically add new responsibilities or behaviors to an object without modifying its original code. The challenge is to extend an object's capabilities in a flexible way that avoids the rigid structure of inheritance, where adding a new behavior means creating an entirely new subclass for every combination of features. Analogy. Think about ordering a coffee. You start with a basic coffee. Then you can decorate it with various additions. Add milk, then add sugar, then add a flavor shot, then perhaps make it takeout. Each addition wraps around the previous one, adding new functionality or modifying the taste presentation without changing the fundamental coffee itself. You don't create a milk sugar flavor shot takeout coffee direct subclass every time. Instead, you layer on improvements. How it works, verbally. The decorator pattern structures a system where a decorator class wraps around an existing component object. Both the component and the decorator implement the same component interface. The component interface defines the basic operations. A concrete component is the original object being extended, e.g., a basic coffee. A decorator is an abstract class that also implements the component interface and holds a reference to another component object. Its methods typically call the corresponding methods on its wrapped component. Concrete decorators are specific decorator classes, e.g., milk decorator, sugar decorator. When a method is called on a concrete decorator, it might perform its own added behavior, e.g., add the milk taste, and then pass the call along to the component it's wrapping. By chaining these decorators, you can add multiple functionalities to an object dynamically. Benefits: flexible extension. New responsibilities can be added to objects at runtime rather than compile time. Avoids subclassing explosion. Prevents the need for a multitude of subclasses just to support different combinations of behaviors. Open-closed principal adherence. Existing code, the concrete component, does not need to be modified to add new features. Facade. The problem: you have a complex subsystem, composed of many classes and objects interacting in intricate ways. Client code that needs to use this subsystem finds it daunting to interact with, requiring knowledge of many individual classes and their methods. You want to provide a simplified, unified interface to this complex set of components. Analogy: imagine a complex home theater system. You have a TV, a Blu-ray player, a surround sound receiver, and multiple speakers, all interconnected. To watch a movie, you might need to turn on the TV, switch the TV input, turn on the Blu-ray player, turn on the receiver, set the receiver's input, and adjust the volume. A facade would be like a single watch movie button on a universal remote that, when pressed, orchestrates all these individual actions for you, abstracting away the complexity. How it works verbally. The facade pattern centralizes the complexity within a single class, the facade. This facade class provides a simpler, higher-level interface to the client. Internally, the facade knows which classes within the subsystem are responsible for fulfilling a request, and it delegates the calls to them. The client code only interacts with the facade and never directly with the many individual classes within the subsystem. Benefits: simplifies client interaction, reduces the number of objects clients have to manage, and simplifies the use of complex subsystems. Decoupling decreases the coupling between the client and the parts of the complex subsystem. The client depends only on the facade, not on all the individual classes. Improved readability makes code cleaner and easier to understand because complex operations are encapsulated behind simple method calls. Acts as an entry point, provides a single, clear point of access to a specific subsystem, making it easier to integrate or replace the subsystem in the future. Composite. The problem: you want to treat a group of objects the same way you treat a single object. This often occurs when you have a hierarchy where individual components and collections of components, which contain other components, need to be manipulated uniformly. Analogy: consider a file system on your computer. You can copy a single file. You can also copy a folder, which contains other files and possibly other folders. Regardless of whether you're clicking on a file or a folder, the copy operation seems to work the same way. The file system treats both individual files and composite folders uniformly in many operations. How it works verbally. The composite pattern uses a tree-like structure where all elements, whether individual or composite, share a common interface. A component interface declares operations that are common to both simple and complex objects, e.g., copy, delete, display. A leaf class represents individual objects that have no children, e.g., a file. It implements the component interface directly. A composite class represents a collection of component objects, e.g., a folder. It also implements the component interface, but its methods might iterate through its child components and delegate the operation to them. The composite class typically has methods for adding and removing child components. Client code can then work with any object that implements the component interface, without needing to differentiate between individual objects and compositions of objects. Benefits: uniformity. Allows clients to treat individual objects and compositions of objects uniformly, simplifying client code. Flexibility. Makes it easy to add new types of components or rearrange the hierarchy without affecting existing client code. Tree structures naturally represents whole-part hierarchies. Proxy. The problem: you need to control access to an object or add some extra behavior when an object is accessed, without changing its core functionality. This might be for security, performance optimization, like lazy loading, logging, or remote access. Analogy: think of a security guard at the entrance to a building. You want to enter the building, access the real object. Instead of directly walking in, you first interact with the security guard, the proxy. The guard performs some checks, e.g., verifies your ID, logs your entry, before allowing you to enter the building. The guard represents the building's entrance, but adds a layer of control and additional functionality without changing the building itself. Another example is a credit card. You don't carry large sums of cash. Instead, you carry a card, which is a proxy for your bank account. When you use the card, behind the scenes, the proxy communicates with the actual bank account to facilitate the transaction. How it works verbally. The proxy pattern creates a surrogate or placeholder for another object to control access to it. Both the proxy and the real subject, the actual object, implement the same interface. The subject interface defines the common operations for both the real subject and the proxy. The real subject is the actual object that performs the core logic. The proxy implements the subject interface and holds a reference to a real subject object. When a method is called on the proxy, it can perform additional logic, like access control, caching, logging, before, during, or after delegating the call to the real subject's corresponding method. Sometimes, the real subject is only created by the proxy when it's absolutely needed, lazy initialization. Benefits: controlled access provides a way to add a layer of control, security, or logging around an object. Performance optimization can implement lazy loading, creating the real subject only when needed, or caching to improve performance. Remote proxies simplifies interaction with objects located in a different address space, e.g., on a different computers. Separation of concerns keeps the core functionality of the real subject clean by offloading secondary responsibilities to the proxy. Structural design patterns are invaluable tools for building flexible and maintainable systems. They help manage the complexity of object relationships, ensuring that your system can evolve gracefully and new features can be added without dismantling existing, stable components. By thinking about how objects are arranged and connected, you can build a robust and adaptable software architecture, much like assembling well-designed modules into a grand structure. Orchestrating behavioral design, patterns part 1. After mastering the creation of objects and their assembly into useful structures, the next critical challenge in software design is orchestrating how these objects interact and distribute responsibilities. This is the domain of behavioral design patterns. These patterns are concerned with algorithms and the assignment of responsibilities between objects. They describe communication patterns between objects, making your system more flexible in how objects collaborate. Behavioral patterns help you manage complex control flows, define chains of command, and allow algorithms to vary independently from the clients that use them. They shift our focus from what objects are and how they are built to how they interact and what they do together. They ensure that responsibility is clearly defined and distributed among classes, preventing the God-object anti-pattern we discussed earlier. Let's dive into the first set of powerful behavioral patterns: observer. The problem: you have a situation where one object, often called the subject or publisher, needs to notify a varying number of other objects, the observers or subscribers, when its state changes. The catch is that the subject shouldn't need to know the specific types of observers. It should just broadcast a message and interested parties pick it up. Analogy: think of a newspaper or magazine subscription. When a new edition is published, the subject changes its state. It doesn't need to know each individual subscriber by name or address. It simply creates the new edition and sends it out to its list of subscribers. Each subscriber and observer receives the new edition and can then read it or act upon it in their own unique way. The publisher doesn't care if you read it in a cafe, at home, or if you immediately toss it in the recycling bin. It just delivers the update. How it works verbally: the observer pattern defines a one-to-many dependency between objects. The subject, also called observable or publisher, maintains a list of its observers. It provides methods for attaching, subscribing, and detaching unsubscribing observers. When its internal state changes, it calls a notify method, which iterates through its registered observers and calls an update method on each one. The observer, also called subscriber, is an interface that defines the update method. Concrete observers are specific classes that implement the observer interface. They register themselves with a subject and implement the update method to respond to notifications in their own particular way. This setup ensures that the subject is decoupled from the concrete observers. It only interacts with the generic observer interface. Benefits: loose coupling. Subject and observer are independent. The subject doesn't know about specific observer implementations, and observers can be added or removed without modifying the subject. Broadcast communication allows an object to broadcast changes to multiple, diverse interested parties efficiently. Increased reusability. Subjects and observers can be reused independently of each other. Strategy: the problem: You have a specific task or behavior in your system that can be performed in multiple different ways. For instance, payment processing could use credit card, PayPal, or direct bank transfer. Data compression could use zip, RAR, or gzip. Sorting algorithms could be bubble sort, quicksort, or merge sort. You want to be able to switch between these different algorithms or behaviors at runtime without changing the code that uses them. Analogy: imagine preparing for a trip. You need to travel to a destination. There are many valid strategies for this: driving your car, taking a train, or flying. Each strategy accomplishes the same overall goal, getting to your destination, but uses a different approach. You choose the strategy based on factors like distance, speed, or cost, and you can switch between them, e.g., decide to fly instead of drive, without changing the fundamental act of traveling. How it works verbally. The strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. The context class holds a reference to a strategy object. It's the client that uses a particular strategy. The context object knows when to execute a strategy, but not how to execute it. The strategy is an interface or abstract class that defines a common method for all concrete strategies, e.g., execute payment, compress. Concrete strategies are specific classes that implement the strategy interface, providing their unique implementation of the common method, e.g., credit card payment strategy, PayPal payment strategy. At runtime, the context object can be configured with or switch to a different concrete strategy. When the context calls its strategy method, the behavior depends on the strategy object it's currently holding. Benefits. Algorithm interchangeability allows algorithms to be selected and swapped at runtime, providing flexibility. Eliminates conditional logic, avoids large, complex if-else or switch statements that decide which algorithm to use. Encapsulates algorithms, keeps each algorithm in its own class, making them easier to understand, test, and maintain. Adheres to open-closed principle. New strategies can be added without modifying the context or existing strategies. Command. The problem: you need to encapsulate a request as an object. This allows you to parameterize clients with different requests, queue requests, log requests, and support undoable operations. Often seen in applications with undo-redo functionality, macro recording, or task scheduling. Analogy: think of a universal remote control. When you press a button, say play on a DVD player, you're sending a command to the player. The remote control doesn't care how the DVD player plays, only that it can play. The play button sends a standardized instruction. This command can be queued up, e.g., press play several times in a row, and the player might respond to each press sequentially, or logged, the remote could keep a history of button presses, and in some advanced remotes perhaps even undone. E.g., if you accidentally change the channel, you could undo that command. How it works verbally. The command pattern involves 4 main components. The command interface declares an execute method. Concrete commands implement the command interface. Each concrete command encapsulates a request to an object. It stores both the receiver object and the action to be performed, and sometimes the parameters for that action. When its execute method is called, it performs the action by calling a method on its receiver. The receiver, the object that actually performs the operation when summoned by a command. A receiver could be almost any object, such as a light object that has turn-on and turn-off methods. The invoker holds a command and at some point tells the command to execute. The invoker doesn't know anything about the concrete command or its receiver, only that it can execute something that implements the command interface, e.g., a button on a remote control. Benefits: decouples sender from receiver. The invoker doesn't need to know anything about the receiver or the specific action. It just knows how to trigger a command. Supports undo-redo. By storing a history of command objects, it's possible to implement undo functionality by reversing the execute operation. Each command would need an undo method. Queuing and logging. Commands can be stored in a queue for asynchronous execution or logged for auditing recovery. Macro recording. A sequence of commands can be recorded and replayed. Iterator. The problem: you need a way to access the elements of a collection, like a list, array, or tree, sequentially without exposing its internal structure. Different types of collections might store their data in very different ways, but consuming code should be able to traverse them uniformly. Analogy: imagine trying to browse items in a shopping cart. Whether it's a physical cart you look into or an online cart where items are stored in a database, you want to be able to go through each item one by one. What's the first item? Okay, what's the next? Is there another one? The way the items are physically stored, stacked haphazardly, or perfectly ordered doesn't matter to you, the shopper. You just need a way to move from one item to the next until you've seen them all. A shopping cart iterator would allow you to do exactly that. How it works verbally. The iterator pattern defines an interface for accessing and traversing elements in a collection, abstracting away the underlying storage mechanism. The iterator interface defines methods like hasNext to check if there are more elements and next to retrieve the next element. It might also include a reset method. The concrete iterator implements the iterator interface for a specific collection type. It keeps track of the current position during traversal. The aggregate interface, or collection interface, declares a method for creating an iterator object, e.g., create iterator. The concrete aggregate, or concrete collection, implements the aggregate interface and provides an implementation of create iterator. That returns an instance of the appropriate concrete iterator for its data structure. Client code requests an iterator from the collection object and then uses the iterator methods hasNext, next, to traverse the collection without knowing how the elements are actually stored. Benefits: separation of concerns. The traversal logic is separated from the collection itself, keeping the collection focused on its data management. Uniform traversal allows clients to iterate over different types of collections, e.g., lists, trees, hash maps, using a common interface. Improved flexibility. New traversal methods can be added by creating new concrete iterator classes without modifying the collection. Secure access prevents clients from needing to expose or manipulate the internal structure of the collection. These behavioral patterns address fundamental challenges in how objects interact and how responsibilities are distributed. They are crucial for building systems that are not only functional but also flexible, decoupled, and easy to extend or modify. In the next chapter, we will continue our exploration of behavioral patterns, delving into more sophisticated interaction models. Orchestrating behavioral design patterns part 2. Our journey through behavioral design patterns continues. Having explored patterns that manage communication, algorithm selection, request encapsulation, and collection traversal, we now turn our attention to more complex scenarios of object interaction and state management. These patterns offer sophisticated solutions for handling dynamic behavior, defining algorithmic skeletons, centralizing communication, and processing requests along a chain. Let's delve into the next set of powerful behavioral patterns. State. The problem: an object's behavior needs to change significantly when its internal state changes. This is more than just a simple conditional check. The entire set of operations available on the object, or how those operations are carried out, depends entirely on its current condition. Without a pattern, this often leads to large conditional statements, if-else or switch spread across the object's methods, making the code hard to read, maintain, and extend when new states are introduced. Analogy: consider a traffic light. Its behavior emitting light changes depending on its internal state, red, yellow, or green. When it's in the red state, its display method shows a red light. When it transitions to yellow, its display method shows yellow, and its next state logic moves it to green. When it's green, its display method shows green, and its next state logic moves it to yellow. The traffic light object's actions are entirely determined by its current color, and the transitions between colors also change its future behavior. You don't have one giant method with if color is red, then do this. Else if color is yellow, then do that. How it works verbally. The state pattern allows an object to alter its behavior when its internal state changes, making it appear as if the object has changed its class. The context: the object whose behavior changes, e.g., traffic light, maintains a reference to a state object. It delegates state-dependent requests to this state object. The state is an interface or abstract class that defines the methods that vary by state, e.g., handle request, next state, display. Concrete state classes implement the state interface, each providing a specific behavior for a particular state, e.g., red light state, yellow light state, green light state. Each concrete state knows how to transition the context to its next state. When the context receives a request, it forwards it to its current state object. The state object then performs its specific action and, if necessary, changes the context's current state to a different concrete state object. Benefits: encapsulates state-specific behavior. Each state's behavior is encapsulated in its own class, making the design cleaner and easier to understand. Eliminates large conditional statements. Removes the need for branching logic based on the object's state, simplifying the context class. Easier to add new states. New states can be added by creating new concrete state classes without modifying existing code. Adheres to open-closed principle. Open for extension, new states, closed for modification, existing context. Template method. The problem: you have an algorithm where the basic structure or skeleton remains constant, but certain steps within that algorithm can vary. You want to define the overall algorithm once and allow subclasses to provide their own specific implementations for the varying steps without altering the algorithm's fixed sequence. Analogy. Imagine a general recipe for baking a cake. The overall steps are fixed: prepare ingredients, mix ingredients, bake, decorate. The bake step might be standard, e.g., 30 minutes at 350 degrees. However, the prepare ingredients, mix ingredients, and decorate steps can vary significantly depending on whether you're making a chocolate cake, a vanilla cake, or a carrot cake. The template method defines the fixed baking sequence, while leaving specific implementation details of certain steps to the individual cake types. How it works: verbally. The template method pattern defines the skeleton of an algorithm in a method, deferring some steps to subclasses. The abstract class, or abstract cook, defines the template method, e.g., bake cake. This method calls a sequence of other methods, some of which are abstract, to be implemented by subclasses, and some are concrete, fully implemented in the abstract class. It might also include hook methods that do nothing by default, but can be overridden by subclasses for optional steps. Concrete classes, e.g., chocolate cake baker, vanilla cake baker. Extend the abstract class and implement the abstract steps, providing their specific variations for those steps, e.g., actually selecting and preparing chocolate ingredients for prepare ingredients. The client code calls the template method on a concrete class instance, and the overall algorithm unfolds using both the fixed steps from the abstract class and the specialized steps from the concrete class. Benefits: code reuse. Common parts of an algorithm are implemented once in the abstract class. Controlling algorithm flow ensures that the overall algorithm structure remains consistent, preventing subclasses from changing the fundamental sequence. Flexibility allows subclasses to provide their specific implementations for certain steps, enabling variation. Enforces consistency, ensures that all concrete variations of the algorithm adhere to the same basic structure. Mediator. The problem: you have a system where many objects interact with each other directly, leading to a tangled web of dependencies. If an object's behavior changes, it might trigger changes in many other objects, and those changes might trigger still more, creating a cascade and making the system difficult to understand, maintain, and test. Analogy. Consider an airport control tower communicating with various airplanes on the runway and in the air. Without a control tower, the mediator, every plane would have to broadcast its intentions to every other plane: I'm landing, I'm taking off, I'm taxiing to gate B2, leading to chaos, collisions, and a huge amount of unnecessary direct communication. The control tower centralizes this communication. Planes only talk to the tower. The tower then relays necessary instructions or information to other relevant planes, greatly reducing direct dependencies between the aircraft. How it works: verbally. The mediator pattern defines an object that encapsulates how a set of objects interact. Instead of objects communicating directly, they communicate through the mediator. The mediator interface declares a method for communicating with colleagues. The concrete mediator implements the mediator interface. It knows about all its colleague objects and how they should interact. It orchestrates the communication between them. Colleague classes, or components, are the objects that interact. They only send and receive messages through the mediator, and they have a reference to their mediator. They are no longer directly aware of other colleagues. When a colleague needs to interact with another, it sends a message to its mediator. The mediator then decides which other colleague, or colleagues, should receive the message and how to route it. Benefits: reduces coupling. Objects are decoupled from each other, knowing only their mediator. This leads to a more flexible and easily maintainable system. Simplifies object interaction. Communication logic is centralized in the mediator, simplifying the colleague objects. Improved reusability. Colleague objects can be reused more easily because they aren't tied to specific other colleagues. Easier to modify. Changes to interaction logic are localized within the mediator. Chain of responsibility. The problem: you have a range of requests, and different types of requests might be handled by different processing objects. You want to avoid coupling the sender of a request to its receiver, allowing multiple objects to have a chance to handle the request. This means a request can be passed along a chain of potential handlers until one of them is able to process it. Analogy: think of customer service or tech support. When you call with an issue, your call might first go to a frontline support agent. If they can't resolve it, they escalate it to a Tier 2 specialist. If that specialist can't help, they might escalate it further to an engineering team. The request, your problem, is passed along a chain of increasing expertise until it finds a handler capable of resolving it. You, the customer, don't need to know who specifically will handle your request, only that it will be processed by someone in the chain. How it works: verbally. The chain of responsibility pattern creates a chain of receiver objects for a request. Each receiver in the chain either handles the request or passes it to the next receiver in the chain. The handler interface, or processor or support agent, declares an interface for handling requests and, optionally, a method for setting the next handler in the chain. Concrete handlers: Tier 1 support, Tier 2 specialist, engineering team, implement the handler interface. Each concrete handler typically stores a reference to its successor. When a request comes in, a concrete handler decides either to handle the request itself or to forward it to the next handler in the chain. The client sends a request to the first handler in the chain. The request travels along the chain until a handler processes it, or until the end of the chain is reached without any handler processing it. Benefits: decoupling sender from receiver. The client doesn't need to know which specific object will handle the request. Flexible responsibility assignment. Objects' responsibilities can be changed at runtime by reconfiguring the chain. New handlers can be easily added or removed. Single responsibility principle. Each handler is responsible for a specific type of request, promoting granular responsibilities. Dynamic behavior. The chain can be assembled and reconfigured dynamically, introducing new processing flows. These behavioral patterns, together with those covered in the previous chapter, constitute a powerful arsenal for designing flexible, maintainable, and robust software systems. They provide proven ways to manage interaction and distribute responsibilities, ensuring that your objects collaborate efficiently and your system can adapt to changing requirements without succumbing to the dreaded tangle of spaghetti code. Understanding these patterns allows you to build systems that are not just functional, but truly elegant in their design. From mess to masterpiece, refactoring with patterns. Up to this point, we've explored the world of design patterns as powerful solutions for building new, well-structured software. And we've illuminated the pitfalls of anti-patterns that plague code bases. But what about the vast majority of software development time, which is spent not on greenfield projects, but on maintaining, extending, and most importantly, improving existing code? This is where the art of refactoring truly shines, and it's where design patterns often provide the proven remedies for ailing code. Refactoring is the process of restructuring existing computer code, changing its internal structure without changing its external behavior. It's like tidying up a messy room or renovating a building. You're not adding new furniture or extending the building, but you're making it cleaner, more organized, and more efficient. The goal is to make the code easier to understand, cheaper to modify, and less likely to contain bugs. The primary motivators for refactoring are often those code smells we discussed earlier, which are symptoms of underlying design problems. When you encounter a long method, duplicate code, a class with too many responsibilities, or a class that seems to be doing too little, these are often signals that a design pattern could be applied to improve the situation. Detecting code smells and identifying anti-patterns. Before you can refactor, you need to identify what needs refactoring. This involves cultivating an eye or an ear for the audio listener for code smells. These smells aren't always glaring errors. They're often subtle indications of disorganization or a lack of clarity. Let's revisit some common code smells and link them to the anti-patterns and the types of patterns that can provide remedies. Code smell, long method/large class, underlying anti-pattern, often a symptom of the God object or a general violation of the single responsibility principle. A method or class tries to do too much. Refactoring aim. Break down the method class into smaller, more focused units. Pattern remedies. Strategy. If parts of the long method contain different algorithms that can be swapped out, encapsulate them as separate strategies. Command. If the method is orchestrating a series of actions, perhaps those actions could be encapsulated as commands. Template method. If one part of the method is a fixed algorithm, but some steps vary, extract the fixed part into a template method in a base class, allowing custom steps in subclasses. Mediator. If the class is orchestrating complex interactions between many objects, offload that coordination to a separate mediator. Facadum. If the large class is really trying to simplify a complex subsystem, make it a dedicated facade and create the underlying smaller classes it manages. Single responsibility principle, the core principle to apply. Break the class down such that each new class has only one reason to change. Each new responsibility might become its own helper class. Code smell, duplicate code. Underlying anti-pattern, copy-paste programming. This is a direct sign that code reuse has been ignored or poorly implemented. Refactoring aim, consolidate repeated logic into a single, reusable component. Pattern remedies. Template method. If multiple pieces of code share a similar structure but differ in details, abstract the common structure into a template method. Factory method, abstract factory. If the duplicated code involves creating similar but slightly different objects, centralize that creation in a factory. Strategy. If the duplicated code represents different variations of an algorithm, encapsulate each variation as a strategy. Inheritance composition. The most direct refactoring often involves extracting a common superclass or creating a new class that the duplicated code can delegate to. Code smell. Many conditional statements, e.g., if else or switch on a type field. Underlying anti-pattern. A sign of violating the open-closed principle or an inappropriate use of inheritance where polymorphism would be better. Refactoring aim, replace conditional logic with polymorphism. Pattern remedies. Strategy. If the conditions determine which algorithm to use, encapsulate each algorithm in its own strategy class. State. If the conditions depend on an object's internal state and determine its behavior, use the state pattern to put behavior into state-specific objects. Factory method. If the conditions determine which object to create, use a factory method to centralize and manage object creation. Code smell, feature envy, underlying anti-pattern. The God object or simply poor distribution of responsibilities. A method in one class spends more time interacting with another class's data than its own. Refactoring aim, move the method or parts of it to the class it's envious of. Pattern remedies, move method class. This is a direct refactoring technique. Delegation. If the method can't be moved entirely, perhaps the logic can be delegated to a new method on the envious object. Code smell, shotgun surgery. Underlying anti-pattern often results from copy-paste programming or a general lack of cohesion. Making one change requires making small changes in many different places. Refactoring aim. Consolidate multiple small changes into one larger change in a single, well-defined place. Pattern remedies. Facade. Create a facade to provide a single, simplified interaction point for a subsystem. Mediator. Centralize communication logic that is currently scattered. Observer. If changes need to be propagated to many places, use Observer to manage the notification process from a central subject once the subject changes. A conceptual walkthrough of refactoring with patterns. Let's consider a common scenario, a simple order processing system. Initial situation, code smell, long method, many conditionals. Imagine a process order method inside an order service class. This method takes an order object and contains a huge if else or switch statement based on the order type, e.g., online, phone, in-store. Each branch of the if else handles all aspects of processing that specific order type. Calculating shipping, applying discounts, updating inventory, and sending a confirmation email. Conceptual representation of the smell. Class order service. Public void process order, order. If order type equals online, calculate online shipping, apply online discount, update online inventory, send online confirmation email. Else if order type equals phone, calculate phone shipping, apply phone discount, update phone inventory, send phone confirmation email. Else if order type equals in-store, calculate in-store shipping, maybe none, apply in-store discount, update in-store inventory, send in-store confirmation email, maybe none. More order types. Problem identified. God object tendency. The order service is becoming a God object having too many responsibilities. Violates SRP. It has multiple reasons to change: shipping logic changes, discount logic changes, email logic changes, or a new order type is added. Violates OCP. Adding a new order type requires modifying this central process order method. Spaghetti-like logic, hard to read and maintain due to sprawling conditionals. Refactoring strategy, applying the strategy pattern. Extract interface for processing. Create an interface I-order processing strategy with a method process, order. Create concrete strategy classes. For each order type, create a separate class that implements I-order processing strategy and encapsulates all the specific logic for that order type. Online order processing strategy. Phone order processing strategy. In-store order processing strategy. Refactor order service. The context. The order service no longer contains the if else monster. Instead, it gets a way to select and hold an instance of I-order processing strategy. It might use a factory method to create the correct strategy based on the order type. For example, order processing strategy factory get strategy order type. Then, it simply calls selected strategy.process order. Resulting structure. Conceptual representation after refactoring. Interface, I-order processing strategy. Void process, order. Class online order processing strategy implements I-order processing strategy. Public void process, order. Online specific logic. Class phone order processing strategy implements I-order processing strategy. Public void process, order. Phone specific logic. Other concrete strategies. Class order processing strategy factory, a simple factory method. Public I-order processing strategy get strategy, string order type. If order type equals online, return new online order processing strategy. If order type equals phone, return new phone order processing strategy. Return null or throw error. Class order service, the context. Public void process order. I-order processing strategy. Order processing strategy factory get strategy, order type. If strategy, null. Strategy.process order, else. Handle unknown order type. Benefits of refactoring. Cleaned up order service. It's now much smaller, focused, and adheres to SRP. Its single responsibility is delegating order processing. Improved OCP. To add a new order type, you simply create a new I-order processing strategy implementation and update the order processing strategy factory. You don't touch the existing order service or other strategies, greatly reducing the risk of introducing bugs. Enhanced testability. Each strategy class can be unit tested independently. Better readability. The intent is clearer. When you see strategy.process, order, you know what's happening at a high level. The iterative nature of improving existing code. Refactoring is not a one-time event. It's a continuous practice. It's an iterative process, much like tending a garden. You don't just plant once and walk away, you continuously weed, prune, and nourish. Small, controlled steps. Refactor in small, safe steps. After each small change, run your tests to ensure you haven't broken anything. Tests are your safety net. A robust suite of automated tests is absolutely essential. They provide the confidence to make changes without fear of introducing regressions. Continuous improvement. Incorporate refactoring into your daily development workflow. Don't wait for a dedicated refactoring sprint, which often never materializes. Shared understanding. Discuss with your team what code smells you see and what patterns might resolve them. This fosters a shared understanding of good design. Transforming a messy code base into a masterpiece is a skill born from practice and a solid understanding of design principles and patterns. Design patterns provide not just elegant solutions for new code, but also a rich vocabulary and proven structure for diagnosing and curing the ailments of existing code. By learning to identify code smells and knowing which patterns can serve as remedies, you can systematically improve the quality, maintainability, and longevity of your software. Piece by piece, turning that spaghetti into neatly organized and highly effective modules. The pattern paradox, when to use and when to avoid. We've now explored a rich tapestry of design patterns, marveling at their elegance and ability to solve common software design problems. They offer proven blueprints for building flexible, maintainable, and robust systems. However, like any powerful tool, design patterns are not silver bullets. Their indiscriminate application can sometimes lead to overly complex, convoluted designs, creating new problems instead of solving existing ones. This chapter explores the pattern paradox, recognizing when a pattern is genuinely beneficial and when it might be an unnecessary burden. Patterns are not silver bullets. The costs and benefits. While design patterns offer significant benefits, it's crucial to understand that they also come with a cost. Benefits of using patterns. Proven solutions. Patterns represent solutions to recurring problems that have been tested and refined by countless developers over decades. Shared vocabulary. They provide a common language for developers to discuss design challenges and solutions, improving communication and collaboration. Improved maintainability and extensibility. Properly applied patterns lead to more modular, flexible, and understandable codebases that are easier to modify and extend. Reduced complexity, when appropriate. By abstracting common problems, they can simplify the overall system design. Faster development, long-term. While initial application might take thought, using established patterns can accelerate development by avoiding reinvention of the wheel and reducing the likelihood of architectural mistakes. Costs of using patterns. Increased complexity, when inappropriate. Over-engineering is a real risk. For simple problems, a pattern can introduce unnecessary layers of abstraction, additional classes, and more boilerplate code, making the system harder to understand than a simpler, direct solution. Learning curve. Developers unfamiliar with a pattern might struggle to understand code that uses it, requiring more time for onboarding and knowledge transfer. Misapplication. Applying the wrong pattern or applying a pattern incorrectly can lead to convoluted and brittle designs that are worse than the problem they aimed to solve. Effort overhead. Implementing a pattern often requires more initial setup and thought than a straightforward approach, which is a trade-off for long-term flexibility. The principle of you ain't gonna need it, YAGNI, and its relevance to patterns. One of the guiding principles of agile software development is YAGNI, which stands for you ain't gonna need it. This principle advocates for not adding functionality until it's actually required. The same philosophy applies beautifully to design patterns. Don't design for hypothetical future needs. It's tempting to foresee every possible future extension and preemptively slap on patterns like strategy or factory method, just in case the requirements change. But more often than not, these predicted future needs never materialize, leaving you with an overly complex solution for a problem you never had. Simpler is better until it isn't. Start with the simplest solution that meets the current requirements. If, and only if, the requirements evolve to a point where the simple solution becomes difficult to maintain, inflexible, or introduces significant code smells, then consider refactoring to introduce a pattern. This aligns perfectly with the iterative nature of refactoring discussed in the previous chapter. For example, don't implement a full-blown factory method if you currently only create one type of object and foresee no need for variations in the near future. A simple constructor call is perfectly fine. If later on, you need to introduce different types of objects with a shared creation process, then you refactor to a factory method. This approach minimizes upfront complexity and ensures that patterns are introduced out of necessity, not speculation. Understanding context, team size, project phase, long-term vision. The decision of whether or not to apply a design pattern is rarely black and white. It heavily depends on the context of your project. Team size and experience. Small, inexperienced teams might benefit from simpler, more direct solutions initially, even if they're not overtly patterned. Introducing too many complex patterns can overwhelm new developers and slow down progress, leading to frustration. Focus on core OOP principles, SRP, encapsulation before jumping into advanced patterns. Large, experienced teams can leverage patterns effectively. A shared understanding of patterns allows for quicker onboarding, better communication, and more consistent design across a large codebase. Patterns become a powerful tool for coordinating development effort. Project phase and lifecycle, early prototype phase, prioritize speed and functionality over perfect design. Over-engineering with patterns in a prototype can stifle innovation and make quick iterations difficult. Get something working, prove the concept, then iterate and refactor. Mature maintenance phase, this is often where patterns shine. As a system grows and evolves, the flexibility and maintainability offered by patterns become invaluable. Refactoring anti-patterns into proper pattern-based solutions can significantly reduce technical debt and improve long-term sustainability. Long-term vision and expected change. Stable systems. If a component or system is expected to be relatively stable with few changes, an overly flexible pattern might be overkill. Evolving systems. For components that are expected to undergo frequent changes, extensions, or variations, patterns like strategy, factory method, decorator, or proxy can be extremely beneficial in accommodating those changes gracefully without constant rewrites. Understanding the likely vectors of change is key. Avoiding over-engineering, finding the balance between flexibility and complexity. The core tension in applying design patterns lies in balancing flexibility with complexity. Flexibility is not free. Every layer of abstraction, every extra interface, every additional class, while potentially adding flexibility, also adds complexity. It means more files to navigate, more indirection to follow, and more concepts to grasp. The Goldilocks principle: you want a design that's just right. Not too simple, rigid, and hard to change, and not too complex, over-engineered, and hard to understand maintain. Analyze the problem, not the pattern. Before reaching for a pattern, clearly understand the problem you're trying to solve. What are the current pain points? What are the real anticipated changes? Start simple and evolve. Adopt an iterative approach. Build a functional solution first. As code smells emerge, or as requirements truly demand more flexibility, then look for a pattern-based refactoring solution. This often leads to designs that are naturally flexible because they've been proven to need it, rather than arbitrarily flexible for every possible scenario. Document your choices. If you do apply a pattern, especially a less obvious one, consider adding a brief comment or documentation explaining why that pattern was chosen and what problem it solves. This helps future maintainers understand the design intent. Ultimately, patterns are tools. A carpenter doesn't build every house out of only hammers or only saws. They choose the right tool for the job. Similarly, a skilled software architect understands the strengths and weaknesses of each pattern and applies them judiciously, driven by concrete problems rather than theoretical elegance. The goal is to build robust software, not merely software that uses many patterns. Good design is characterized by simplicity and clarity that effectively solves the problem at hand, making it understandable, maintainable, and adaptable for future needs. The true mastery of patterns lies not in knowing how to implement them, but in knowing when and why to use them, and equally important, when not to. Beyond code architectural anti-patterns. So far, our discussions have largely centered on anti-patterns that manifest directly in code, like the God object or spaghetti code. These are critical to understand for individual software components. However, the quality of a software system isn't solely determined by the purity of its code. Design flaws can extend much further, infecting the entire project, impacting teams, and even influencing an organization's strategic choices. These are architectural anti-patterns, recurring negative solutions or common pitfalls that occur not just within the lines of code, but at the higher levels of system design, project management, and organizational culture. Recognizing these broader anti-patterns requires a different lens, moving beyond technical syntax to consider the human element, business pressures, and long-term consequences. Ignoring them can lead to project failure, massive technical debt, and a demoralized workforce, even if the individual code components are well-crafted. Architecture astronaut. The problem: this anti-pattern describes an architect or designer who creates overly complex, abstract, and theoretical designs that are disconnected from the practical realities of implementation or the immediate needs of the business. They spend too much time designing elaborate, flexible architectures for hypothetical future scenarios, often at the expense of delivering functional software today. Analogy. Imagine a residential architect who designs a house with 7 different types of foundations, a complex network of internal roadways, and a communication system for talking to the house from other planets. While technically impressive in its theoretical scope, it's completely impractical, hugely expensive, impossible to build within a reasonable timeframe, and serves no real purpose for someone who just wants a functional home. The architect is designing for an imagined universe, not the real world. Consequences: analysis paralysis. The project gets stuck in an endless design phase, delaying development. Over-engineering. The resulting system is excessively complex, hard to understand, and expensive to build and maintain, far beyond what the problem requires. Disconnection from reality. The design might ignore real-world constraints like budget, time, available technology, or team skills. Demoralization. Developers often feel frustrated trying to implement an unnecessarily complex and abstract design. Vendor lock-in. The problem: this anti-pattern occurs when a system becomes so dependent on a specific proprietary technology, product, or service from a single vendor that switching to an alternative becomes extremely difficult, costly, or impossible. This dependency often limits flexibility, stifles innovation, and potentially exposes an organization to unfair pricing or terms. Analogy. Imagine buying a car, but the manufacturer uses unique, proprietary parts for everything, from the tires to the engine. You can only buy spare parts and get service from that specific manufacturer. If they decide to double the price of oil changes or stop making your specific tire size, you're stuck, because no other mechanic or parts supplier can help you. You are locked in to that one vendor. Consequences: reduced flexibility, limits choices for future technology stack, preventing adoption of potentially better or cheaper alternatives. Increased costs. The vendor can charge premium prices due to the lack of competition and the high switching costs. Exposure to vendor's fate. Business-critical systems become vulnerable to the vendor's financial stability, roadmap changes, or even bankruptcy. Limits innovation. The organization might be forced to stick with older, less efficient technologies if the vendor doesn't innovate or innovation is slow. Analysis paralysis. The problem: this is a state where an individual or team overanalyzes or overthinks a situation, leading to a point where no decision or action is taken, effectively paralyzing the project's progress. It's often driven by the fear of making a mistake or a desire for perfect information. Analogy. Imagine a chef who spends weeks researching every possible spice, every cooking technique, and every culinary tradition instead of cooking a meal. They might create detailed flowcharts of ingredient procurement and ideal cooking temperatures, but no dish ever leaves the kitchen. The desire for the perfect, or safest, recipe means no food is ever served. Consequences: missed deadlines, projects fall behind schedule due to inaction. Opportunity costs: Valuable time and resources are consumed in endless deliberation rather than productive work. Demotivation. Team members become frustrated by the lack of progress and indecision. Stagnation. The product or system never moves from concept to implementation or moves very slowly. The sunk cost fallacy. The problem: this anti-pattern describes the tendency to continue investing in a failing project or endeavor because of the time, money, and effort already spent on it, even when the rational decision would be to abandon it. The feeling that past investment would be wasted becomes a stronger motivator than the objective analysis of future potential. Analogy. Imagine you've spent a large sum of money and effort building an elaborate, custom-designed boat over several years. You then discover, halfway through construction, that due to a fundamental flaw in its design, it will never actually float. However, because you've already sunk so much time and money into it, you decide to keep pouring more resources into trying to get it to float, rather than cutting your losses and starting a new, feasible design. Consequences: continued waste of resources. Resources that could be put to productive use on new, viable projects are instead thrown into a losing battle. Increased debt. Technical debt, financial debt, and strategic debt continue to accumulate without producing value. Missed opportunities. Other, more promising ventures are ignored while resources are tied up in the failing one. Demoralization. Teams working on a clearly failing project become cynical and unmotivated. The human element. Communication, ego, and decision-making in design. Many architectural anti-patterns, unlike localized code anti-patterns, highlight the profound impact of human factors on software design. Communication breakdown. Poor communication can lead to duplicated efforts, conflicting designs, and a lack of shared vision. An architecture astronaut might emerge if they're not communicating effectively with developers or business stakeholders. Ego and ownership. An architect or lead developer's ego can blind them to valid criticism or alternative approaches, sometimes leading to the golden hammer or reinforcing a god object design. Strong ownership without collaboration can be detrimental. Fear of failure/risk aversion. This can easily contribute to analysis paralysis, with teams being afraid to commit to a direction until every single contingency is accounted for. Organizational silos. Different departments or teams might optimize for their own goals, leading to vendor lock-in or fragmented architectures that don't interoperate effectively. Short-term thinking. Constant pressure for immediate delivery can encourage quick, dirty solutions that lead to spaghetti code or copy-paste programming, accumulating technical debt that the organization will pay for dearly in the long run. Understanding these broader, organizational anti-patterns is crucial for anyone involved in software development, not just architects or senior developers. They underscore that building great software isn't just a technical exercise, it's a social and organizational challenge. By identifying and addressing these human and systemic factors, alongside the technical ones, teams can foster environments that promote sustainable, effective design and avoid the major pitfalls that can derail even the most talented technical teams. The journey of a software architect, cultivating design acumen. We've explored the foundational principles of object-oriented design, delved into the practical solutions offered by design patterns, identified common pitfalls in code, and recognized broader architectural anti-patterns that plague projects. Now it's time to bring it all together. Building quality software is not merely about writing lines of code. It is a holistic endeavor, a continuous journey of learning, adapting, and refining one's approach. Cultivating design acumen means developing an intuitive understanding of what makes software robust, flexible, and maintainable, and being able to communicate that vision effectively. Putting it all together. A holistic view of software quality. A truly excellent software system is not just functional. It embodies a range of quality attributes. Maintainability. How easy is it to fix bugs or make minor changes without introducing new problems? This is directly impacted by good design through clear separation of concerns, readability, and testability. Extensibility. How easy is it to add new features or modify existing ones without fundamentally redesigning the system? Design patterns, particularly those adhering to the open-closed principle, are key enablers here. Reliability. How consistently does the system perform its functions correctly? Robust error handling, effective testing, and well-isolated components contribute to this. Scalability. How well does the system perform under increasing load or data volume? Architectural choices, often guided by patterns, play a major role. Testability. How easy is it to write automated tests for the system? Loose coupling, facilitated by many patterns, e.g., strategy, factory method, dependency inversion, is crucial for isolating components for testing. Understandability. How quickly can a new team member grasp the system's logic and structure? Clear design, consistent naming, and well-applied patterns provide a shared vocabulary that significantly improves comprehension. These qualities are not achieved by accident. They are the direct result of intentional design decisions, often involving the judicious application of patterns and the conscious avoidance of anti-patterns. The individual lines of code are the atoms. The patterns are the molecules that form the fabric of a high-quality system. The role of constructive code reviews and design discussions. Design is rarely a solitary activity, especially in team environments. Collaboration is key, and two of the most powerful tools for fostering good design are constructive code reviews and dedicated design discussions. Code reviews. Beyond catching bugs, code reviews are invaluable opportunities to apply design thinking collaboratively. When reviewing code, instead of just looking for syntax errors, ask, does this code adhere to the single responsibility principle? Could another class become a God object due to this change? Is there an anti-pattern lurking here, e.g., duplicate code suggesting a missed pattern opportunity? Can we apply a pattern here to make this more flexible or maintainable? Is this code easy to read and understand without excessive mental gymnastics? Is this introducing unnecessary complexity, perhaps violating YAGNI? Approach reviews as a mentoring opportunity, not just an audit. Explain why a particular design choice is better, referencing principles and patterns. A well-placed question about a design decision can be far more impactful than a directive. Design discussions. Before writing a significant amount of code for a new feature or major refactoring, dedicate time to design discussions. These aren't just meetings. They are collaborative sessions where ideas are debated, alternatives are explored, and a shared understanding of the problem and proposed solution is built. Focus on the problem. Always start with, what problem are we trying to solve? Explore options, discuss different architectural approaches, sketching out how various patterns might fit. Anticipate change. If the requirements change in this way, how would our proposed solution adapt? This is where patterns truly demonstrate their value. Validate assumptions. Bring different perspectives to the table, developers, testers, product owners, to ensure all angles are considered. Document decisions. Not every detail, but the major design choices and the rationale behind them should be recorded. This is crucial for future reference and for onboarding new team members. These discussions build collective design acumen within a team, ensuring that design principles are consistently applied and that the system architecture remains coherent. Practical steps for improving your design, thinking, and vocabulary. Cultivating design acumen is a lifelong pursuit, not a destination. Here are actionable steps you can take. Read and reread foundational texts. Immerse yourself in the classic books on design patterns, refactoring, and clean code. Every time you revisit them, you'll find new insights as your experience grows. Practice, practice, practice. The only way to truly understand patterns and principles is to apply them. Start small. Pick a feature, design it using a pattern, then try to design it without one and compare the trade-offs. Work through refactoring exercises. Active code smells hunting. When you encounter code, look for smells. When you find one, ask yourself, what anti-pattern does this suggest? And what pattern could resolve this? Even if you don't refactor it immediately, the practice of diagnosis builds your intuition. Engage in design discussions. Participate actively in design discussions. Don't be afraid to ask why or suggest alternatives, even if you're junior. Listen attentively to experienced designers and try to understand their reasoning. Seek and give feedback. Ask for feedback on your designs and code. Be open to constructive criticism. Offer thoughtful, principle-based feedback to others. This reciprocal learning accelerates growth. Learn from mistakes, yours and others. Analyze postmortems of projects that struggled with maintainability or scalability. Often, anti-patterns were at play. Reflect on your own design decisions that didn't work out as expected and learn from them. Explore polyglot programming. Learn another programming language, especially one with a different paradigm, e.g., functional programming. This broadens your perspective and can reveal new ways to think about structuring problems and solutions that might even cross back over into your object-oriented work. Teach and mentor. The best way to solidify your understanding of a topic is to explain it to someone else. Mentor junior developers, contribute to internal training, or write blog posts about design concepts. The importance of continuous learning and adapting to new paradigms. The world of software development is in constant motion. New technologies emerge, existing paradigms evolve, and the problems we solve become increasingly complex. What constitutes best practice today might be obsolete tomorrow. Beyond GoF, while the gang of 4 patterns are foundational, the field has evolved. Explore newer patterns and architectural styles, e.g., microservices, event-driven architectures, serverless patterns. Understand their trade-offs and how they might fit alongside or modify traditional OOP patterns. Functional programming influence. Concepts from functional programming, like immutability and pure functions, are increasingly influencing object-oriented design, leading to more robust and testable code. Embrace these cross-pollinations. Cloud-native design. Building applications for cloud environments introduces new architectural considerations and patterns, e.g., circuit breaker, saga, retry patterns. The journey of a software architect, or indeed any software professional striving for excellence, is one of continuous learning and adaptation. It's about building a robust mental model of software systems, a toolkit of proven solutions, and a keen eye for warning signs. It's about understanding that the code we write today is just the beginning of its life, and good design ensures it can flourish and serve its purpose for years to come. With the compass of design patterns and anti-patterns firmly in hand, you are well equipped to navigate this ever-evolving landscape and contribute to the creation of truly elegant, sustainable software. Your design compass, practical next steps, and resources. As we reach the culmination of our journey through the world of object-oriented programming, design patterns, and anti-patterns, it's important to recap the key takeaways and provide clear, actionable steps for you to continue applying this knowledge. Remember, this book is not merely a collection of definitions. It's a guide to transforming your approach to software development, enabling you to build more resilient, maintainable, and understandable systems. Recap of key takeaways. We began by emphasizing that software design is a craft, not just a technical exercise. Good design fundamentally impacts the longevity, adaptability, and cost of software. The power of patterns. We discovered that design patterns are reusable, proven solutions to common problems in software design. They provide a shared vocabulary, accelerate development by offering pre-tested solutions, and enhance communication within teams. We explored 3 main categories: creational patterns, singleton, factory method, abstract factory, builder, gave us control over object instantiation, decoupling the client from the creation process. Structural patterns, adapter, decorator, facade, composite, proxy, showed us how to assemble objects and classes into larger, more flexible structures, managing complexity and relationships. Behavioral patterns, observer, strategy, command, iterator, state, template method, mediator, chain of responsibility, illuminated how to manage object interactions, distribute responsibilities, and define algorithms elegantly. The wisdom of anti-patterns. Just as crucial as knowing what to do is knowing what not to do. Anti-patterns, God object, spaghetti code, lava flow, copy-paste programming, golden hammer, magic pushbin, are common pitfalls that lead to technical debt, rigidity, and frustration. Recognizing them is the first step towards avoiding or remediating them. Foundational principles, solid. We saw that patterns often embody and support the solid principles: single responsibility, open-closed, Liskov substitution, interface segregation, dependency inversion. which provide a critical framework for designing cohesive, loosely coupled systems. Refactoring as an art. Design patterns are not just for greenfield development. They are powerful tools for refactoring existing code, transforming code smells and anti-patterns into robust, maintainable designs. This iterative improvement process, supported by a strong test suite, is essential for healthy long-term software projects. The pattern paradox. We learned that patterns are not silver bullets. Blindly applying them can lead to over-engineering and unnecessary complexity. The principle of "you ain't gonna need it" YAGNI serves as a vital reminder to introduce complexity only when genuinely required by the problem's context or forecasted evolution. Beyond code, architectural anti-patterns. Finally, we broadened our scope to understand that design flaws extend beyond code into project management and organizational dynamics. Anti-patterns like architecture astronaut, vendor lock-in, analysis paralysis, and the sunk cost fallacy highlight the human and systemic factors that profoundly impact software quality and project success. Cultivating design acumen. We concluded by emphasizing that mastering design is a continuous journey. It requires active participation in code reviews and design discussions, a commitment to continuous learning, and an adaptive mindset to navigate the ever-changing landscape of software development. Actionable steps for applying what you've learned. The true value of this book comes from applying its lessons. Here are concrete steps you can take starting today. Start small. Don't try to redesign your entire system overnight. Pick one small, manageable part of your code base that has a clear code smell or is causing recurring issues. Identify the problem. Ask yourself, what specific problem does this part of the code have? Is it hard to test? Is it difficult to change? Does it have too many responsibilities? Spot the pattern anti-pattern. Can you recognize a specific anti-pattern at play, e.g., this class is doing too much? It's a mini-god object. Can you see how a pattern might offer an elegant solution? E.g., this switch statement could be a strategy. This object creation could use a factory. Experiment and refactor. If you have good tests, try applying a relevant pattern. See how it changes the code's structure, readability, and flexibility. If you don't have tests for that area, write them first. They are your safety net for refactoring. Discuss and share. Talk with your colleagues about the patterns and anti-patterns you're learning. Bring up code smells during code reviews. Discuss design choices in terms of patterns. The more you use the vocabulary, the more natural it will become for you and your team. Read others' code. Actively look for patterns or anti-patterns in open-source projects or your company's code base. How did others solve problems? Were their solutions elegant or messy? Reflect regularly. After completing a feature or fixing a bug, take a moment to reflect. Could I have designed this better? Did I unknowingly fall into an anti-pattern? Could a design pattern have made this easier? Curated list of suggested further reading. This book serves as your initial compass. To truly master the art of software design, you must continue to explore and learn. Here are some foundational and influential texts that will deepen your understanding. Design Patterns. Elements of Reusable Object-Oriented Software by Erich Gamma, Richard Helm, Ralph Johnson, and John Velicides, the Gang of Four or GoF. This is the seminal work. While it focuses heavily on C++ and Smalltalk and can be dense, it's the primary source for the 23 classic design patterns. Reading it will give you a deeper understanding of the patterns discussed here. Refactoring. Improving the Design of Existing Code by Martin Fowler. An absolute must-read for anyone serious about improving code quality. It provides an extensive catalog of specific refactoring techniques and when to apply them, which ties directly into turning code smells into well-designed code. Anti-Patterns. Refactoring Software, Architectures, and Projects in Crisis by William J. Brown, Raphael C. Malvo, Hayes W. McCormick III, and Thomas J. Mowbray. This book provides a broader view of anti-patterns, extending many concepts from our Chapter 10 into deeper analysis of architectural and project-level pitfalls. Clean Code. A Handbook of Agile Software Craftsmanship by Robert C. Martin, Uncle Bob. A highly influential book on writing readable, maintainable, and testable code. It emphasizes many of the principles, like solid, and practices that underpin good design. Head First Design Patterns by Elizabeth Freeman, Eric Freeman, Bert Bates, and Kathy Sierra. If you found the analogies and visual storytelling in this book helpful, you'll love Head First Design Patterns. It's an excellent, highly engaging, and memorable introduction to the GoF patterns, especially helpful for visual learners. Patterns of Enterprise Application Architecture by Martin Fowler. For those working on larger, enterprise-level systems, this book explores architectural patterns and concepts beyond the GoF level. The Pragmatic Programmer, Your Journey to Mastery by Andrew Hunt and David Thomas. A classic broad-ranging book on various aspects of software development, including valuable insights into thinking about code quality and maintainability. Embracing software design as a continuous journey. Your learning doesn't stop here. Software design is not a static academic discipline. It's a dynamic craft that evolves with technology and understanding. Embrace the mindset of a continuous learner. Attend conferences, follow influential practitioners online, participate in online communities, and read articles and papers about new patterns and architectural styles. The Architect's Compass is now in your hands. It provides you with the essential tools and mental models to navigate the vast and complex landscape of software development. Use it to chart a course towards elegant, robust, and maintainable software systems. Your ability to speak the language of patterns and anti-patterns, understand the principles, and apply them judiciously will not only make you a better programmer, but a true software craftsperson, capable of building lasting and valuable applications. The journey is exciting, challenging, and endlessly rewarding. Go forth and design with purpose.